But when we have a short class, when we have a short class like that, it keeps me honest. So that's good. Okay, so let's go ahead and talk about evapotranspiration and calculating it again. Again, there are lots and lots of formulae for calculating rainfall or for calculating runoff and infiltration and things like that, and evapotranspiration. But these are good working models that I want you to become familiar with, and not so much to say, oh, you know, this is the best thing since sliced bread, but it's just a model that you can use so that if somebody kind of said, well, what do you think evapotranspiration is going to be at this time of the year? You can say, okay, what? You know, and go to your notes and say, okay, well, you know, we think it might be this or that or the other. I have a guy who works for the Rural Water Research Foundation, and he was a MERM, but his background was business, and he works in the rural area, and he says, not a week goes by where he doesn't go back to his notes and kind of look stuff up. So that's kind of gratifying. So that's kind of, you're not going to become theoretical physicists coming out of this class. Okay? But, all right, evapotranspiration. Let's first figure out what is evapotranspiration. By the way, this is all found in that Haith and Shoemaker citation that we've got here. And that's online right now. It's the HSPF, Generalized Watershed Loading Function. Okay. So what is evapotranspiration? We've heard of evaporation, and evaporation typically applies to water that evaporates off soils or water that evaporates off lakes and things like that. And it gets pretty high. In the summer, it might be 8-12 millimeters a day around here, depending on the temperature of the water and stuff like that. And that's just off the lake surface. You've got evaporation of soils. But what really kind of drives evapotranspiration, or transpiration, is where plants take water not from the surface water, but it takes water from between soil pores not between soil particles, so in the soil pore spaces, and through the root action and capillary action sucks the water up into the plant itself. Let's say that's a tree, and that goes out, because that keeps the plant or the tree cool, and it also helps in the whole physiological process of photosynthesis and everything else. Because the moment you had to stop this process over here, that tree is going to wilt. So when we get to a point called wilt point in the transpiration process, this tree has simply not got the ability to suck any more water out. And wilt point, actually the tree, most plants can exert up to about 15 atmospheres of suction pressure. Okay, so that's a heck of a wilt point. So in evapotranspiration, and we talked about wilt point last week, didn't we? I think we did. Permanent PWP, permanent wilt point. Okay.
Sounds familiar.
Yeah. So the transpiration is this action over here of the tree pulling stuff up and getting it up into the atmosphere. Evapotranspiration is the combined amount of evaporation from uncovered area and then transpiration over here. What would we expect? I'm going to give you 3 scenarios. This is January to December. Would we expect evapotranspiration to do this, or to do this? So 3, 1, 2. Scenario 1, 2, or 3. This is July in the middle. What's it going to do, evapotranspiration?
3, probably 3.
It's going to be 3, right? So, number one, temperature's up. What else do we find at this time of the year? Biologically. It's an obscure question.
Lower rainfall, lower precipitation?
Okay, that's climatology, but...
Oh, it's a high growth season.
That's the growing season. That's when the plants are growing. So essentially what happens is not only is your temperature increasing, but you've got a lot of plant growth. So in fact, that over a year's time, your evapotranspiration curve actually looks a little bit like a bell curve. And it's going to sort of go from about April or May to September or October. You've got very low amounts of evapotranspiration in the fall, or sort of starting in October through to sort of January to February. You're not going to have that much evapotranspiration happening today. Okay? So that's kind of the big picture if we get out and kind of look back on stand back and look at it. Evapotranspiration is something, is a function of two things. ET is equal to cov times PET. Your cover factor is a factor that is based on, well, let's talk about PET, potential evapotranspiration. And so theoretically, if your soil was absolutely chock full covered with vegetation, you'd be, that cover factor would be basically 1. So you would be getting your absolute maximum of your potential evaporation. So if PET were, say, 9.5 millimeter per day, which would be quite realistic, and your cover factor would be 1, your evapotranspiration would be 1 times your PET. Okay. If your cover, only half of your ground were covered, it would be 0.5 times 9.5, which would be 4.75 millimeter per day. So this is basically, there are two components. The cover factor, if you go ahead and have a look at Hayth and Shoemaker, that thing I gave you, sorry, Taylor, I'll give it, page 29 and 30, you'll see all of the cover factors over here. Sort of, now, Hayth and Shoemaker did this mainly for agricultural areas, but most of those values are actually lower. But it's kind of interesting. So it's a function of cover coefficients. Some of these things over here are actually now higher than 1. So I'm not sure how that works out, but it is what it is.
Does percent of growing season, is that just temporal? So like 0% in this chart is at planting?
Yeah, I think it's, if your growing season is, say, 5 months,
okay,
then
60% into the time of the growing season you have.
Actually, you know, oh yes,
okay,
that would be it. Yeah,
okay.
I think so. In most cases, the guys don't do that. You can see here, your cover coefficients of perennial crops would be here. So there's no temporal thing, although perennials are also going to slow down, but then that's more, the change is more as a function of potential evapotranspiration. And then these are your approximate ratios on table B8. Sorry, I'll give this back to you.
Okay.
Table B8 is your approximate number, you know, so for instance, annual crops in a dormant season versus growing season. So they're basically saying, if you've got annual corn in the growing season, say May through to September, that cover factor is going to be 1. Off season, it's going to be 0.3. That's when you've got like winter weeds and volunteer corn and stuff like that. In urban areas, they have this thing 1 minus L. where L is the, or I is the impervious fraction. So and we've got that in the homework thing for you today. So have a look. So in reality, Stuart, what you're saying in reality is during the growing season, as these plants grow and reach the peak of their life cycle, that's when they're going to be active the most, and then you can see those peaks fall off. So we can get fancy with these things, but again, these numbers are only approximations. The more important, or the more sort of the less uncertain part of this equation is this whole idea of potential evapotranspiration, PE. So let's have a look at that very quickly. PE is this ugly little equation where 0.021 h squared times ET over T plus 273. So this is going to be a function, number one, of PET is a function of, number one, the hours per day. And the hours per day you can look up in this table at the back here. Page 30 in Hayth and Shoemaker. So you can look up, I think we're on 44 North, and you can look up for every month, it calculates how many hours, sorry, not hours per day, hours of daylight per day. Because daylight, hours, daylight. Because daylight is going to determine how much photosynthesis is going to be occurring, right? Okay, the second thing it's a function of is ET, and that's the saturated water vapor pressure in millibars. Okay, and so that's just a long sat water vapor pressure. And that saturated water vapor pressure is going to be a function of temperature. And then that's all over a function of temperature as well. Actually, why it's an inverse over temperature, and I think that's because of your evapotranspirative term. So it's really a question of, do I know what the hours in the day are? Do I know what my temperature is? Then it's a question of basically plugging and chugging into this equation. Okay, and that's all that is. And so you can see rather than my making a fool of myself and relying overly on your calculators, let's rather leave you to look at this potential evapotranspirative equation over here. But it's not that difficult to calculate out. But evapotranspiration is a function of the hours of daylight and essentially of temperature, because your saturated water vapor pressure is a function of temperature. Now, in the homework, I have a spreadsheet where you will need to plug in a couple of numbers. It's sort of, I've done it over 12 months. And so I've given you a place where you plug in, for instance, your daylight hours. I give you a place where you've got to plug in one of two other things. I think I calculate the saturated water vapor pressure for you. And something else there. Oh, I think I get you to calculate PET as well. So you've got to just find those numbers, and it's just kind of plug and chug. And what I've got in the spreadsheet is also a built-in graph. So as you chart it, you'll be able to see what happens. And I think I give you a couple of scenarios. One scenario would kind of look like this, and the other scenario would kind of look like this. Okay, so actually no, I think they're both. So you can have a look at those things. So that that wasn't exactly much over there. I'm going to, rather than try and force in a talk on the link between soil quality or soil function and water quality, I'm going to give you a URL to look at, and just my friend Ray Archuleta talks about it. But let me give you a kind of just a few thoughts on soil function, what soil function is about. Okay, first of all, questions on evapotranspiration. It's kind of plug and choke, okay, but I'm just putting it out there so that you guys can see what it is. And you know, now that you know how to calculate runoff and infiltration from a given rainfall, now that you know how to calculate evapotranspiration, you can actually now start getting a decent handle on a mass balance, a watershed balance, you know, in a watershed. Because those are basically the numbers that you'd be looking at. Let's go ahead and just talk about this notion of soil function. Okay, we've talked about one of the aspects of soil function has been the ability of soil to infiltrate water. Another soil function is the ability of soil to hold water. Usually that's a function of soil type or soil texture, the mixture of sand, salt, and clays, but it's also a function of how much organic matter is in that soil. And the less disturbed soils are, the more organic matter they have, the more organic matter they have, and the less disturbed they are, the more pore space they have. The more pore space they have, the more ability they have to retain water. And the actual organic matter in them as well provides them with sort of that ability to sponge up that water. Okay, so soil function, the soil functions that we kind of care about in this class would be the ability of the soil to infiltrate water, and the soil then also to hold the water in place. Other soil functions would be, you know, sort of on a global basis, it's a place that you store carbons. Another soil function might be that soils break down harmful organic chemicals because of the biology in the soils. So those are also functions that soils provide for us. But you know, if you go out into the Midwest, you find that they have these very deep organic soils, the prairie soils, called mollisols, which are like kind of the Rolls Royce of soils. You know, you go ahead, they used to go ahead and plow these things up, and they would plant, and the corn would just grow high. And even if they haven't got any rain, you know, these soils are like 15, 20 foot deep, and every drop of rain falls in, and it gets sucked up, and these were highly functioning soils. Over time, though, what happened was, you know, they would leave them fallow in the winter, and 2-3 inches a year of soil would wash away. And so what was happening is that the soils began to degrade, the organic matter went away, and what was left was more and more mineral matter, and the soils became shallower and shallower. So what was originally the Rolls Royce of soils eventually ended up firing, instead of firing on 8 or 12 cylinders, it was firing on 2 or 3 cylinders. So theoretically a good soil if undisturbed, not a good soil if disturbed. Whereas down here, up there, you know, they would typically have 5% of soil organic matter. Down here, some of these Piedmont soils are not very well drained. They're very shallow, and you know, they're nothing like the soils of the Midwest. Over here, you know, the organic matter came from the leaf litter and things like that, where over there, most of the organic matter came from these deep prairie grasses that grew there. But it's possible for a soil to be better functioning over here if you treat it correctly, compared to one of those really, really good soils out there. So you could, in other words, they might have a Cadillac up there, but if the Cadillac's firing on all 4 cylinders and you've got a 1974 Beetle in mint condition, that 1974 Beetle might still be able to beat the Cadillac just because it's been treated right. So that's the notion of soil function. And soils have the ability to function better and better if we do not disturb them, and if we learn how they function, and if we learn how to improve their function. And improving function is doing things like diversity, never trying to grow the same thing over and over again. Keeping the soil covered, never allowing soils to be naked. Keeping a live root in the ground all year. So those principles you can apply to soils to actually increase their function and increase the ability of soils to actually infiltrate and retain water. Do you remember the sort of general rule of remember we talked a little bit in general, erosion. Soil erosion is proportional to runoff, let's say to about the power of 4, to the power of 3, 4, I've heard different numbers. But what it's telling you is that as our runoff, even if our runoff were to increase by a small amount, it's going to have a disproportionate effect on soil erosion. Okay. So when we start disturbing soils, we're increasing this runoff factor, which in turn increases this. And when we have soil erosion, what often happens is there's preferential loss of the finer particles and the lighter particles. The finer particles being the clays, and the lighter particles being the organic matter. So what that means, the lighter particles and the finer particles are actually the ones that make the soil more chemically active and more friendly to plants. So what it often means is kind of you're left with the heavier fractions and the larger fractions. More gravel, more sand, that kind. Less organic matter, less clay. And so that then sort of becomes a vicious cycle. And I think we talked last time, something like from the beginning of this talk till now, we lose about 6.5 trillion tons of soil in the United States. And if you kind of calculate that out, in 1 hour, that means we lose about 750,000 tons of soil from unprotected land, either tilled or really, really poor construction jobs. They put up those silt fences, and it's such a joke. Okay, so if you kind of boil it all down, it comes down to this whole thing. Ray does some great sort of on-stage experiments. But soils basically are held together and in fact also held apart by these sticky networks of fungal hyphae, by little particles by roots, by little particles of organic matter, humus and stuff like that. It becomes an incredibly sticky network where there's lots and lots of space between the soil particles. And Ray Archuleta often talks about our job is to actually manage that pore space. So as an environmentalist, as an environmental scientist, when we're trying to talk about increasing infiltration or reducing runoff, what we're trying to do is begin to manage that pore space. Because Ray talks about things like riparian buffers. He calls riparian buffers diaper practices. Okay, because if you've got to put a riparian buffer in, something upland is causing that runoff. You should be stopping that runoff before it actually comes into those diaper practices. And often those diaper practices just get overwhelmed. You know, if you have a 150-foot riparian buffer, but you know you've got 15-acre shopping mall and you know really badly looked after streets, and you know people do all sorts of crazy things in the garden so that they have nice lawns and stuff like that. There's a lot of runoff that goes in there, and that riparian buffer has no chance at all. Okay, so it's about looking after that pore space. Ray is a very entertaining guy, so I'll let him talk to you rather than let me talk to you. I think that's all right now. I'll send you that URL. You guys can look at it. Homework, there's not that much of it.